So it turns out that Faraday's law of induction is actually very important to our technology. For example, it's how we do a conversion of energy from mechanical energy into electrical energy. Let's look at a schematic version of the simplest version of one of those devices, which is an AC generator. So you start with a magnet or magnets that produce a permanent magnetic field. And then we're going to put in a coil. And that's just a coil of wire, and what we're going to do is we're going to rotate it around its axis. And because we've got this area of coil, and we're turning it through the magnetic field, and what that's going to do is change the magnetic flux that's going through that coil. The magnetic field's going to be constant. The actual area of the coil is of course constant, but the angle is changing, and therefore the perpendicular area is changing. Indeed, it's changing sinusoidally. So this A loop is the total area of our loop here, but it's changing sinusoidally because the angle is changing. The angle is going to go through 2 pi radians every time we go through a period. And so that cosine has to be 2 pi radians every time we go through a period, so time divided by period. So obviously that flux is changing, and so obviously it's going to be time dependent, and therefore it's going to produce a voltage in that coil. And if you put many turns on that coil, then you'll get a stronger voltage in that coil. If we look at the flux as a function of time, if we start at time equals 0, cos of 0 is 1, and so we start at the maximum of the magnetic field times the total area of the loop, and then cos just goes like this. Now if we want to see how that flux changes in time, we have to look at the slope of this graph, and we can see that initially it doesn't have any slope at all, and so this will be 0. So while the coil is in this position, there will be no voltage through the coil. But then when we get to here, we'll have quite a high slope, and then at this point we'll have none again, and then a strong slope going the other way, and then none, and so on. And so we can see at the point where the slope is the maximum in the negative direction, we've got a maximum slope there, and when it's flattened out, we have 0 change in our magnetic flux, and then we've got our maximal change, and so on. And of course, the change in the magnetic flux is precisely just proportional to the voltage. And therefore, this is a picture of the voltage we're going to get out. If we do that mathematics properly, we'll find that that's also a sinusoid, and you'll see that it's alternating. And that's why this is called an AC generator. It's also known as an alternating current generator. This is actually how all our power is transmitted. In Australia, the frequency at which this is oscillating is 50 Hertz, 50 times a second. Now some devices don't like the potential to oscillate like that. They like a nice constant potential. And those are called direct current devices, DC. And to make a DC generator, what you do is you basically take an AC generator and cheat. So all the business end of the generator with the magnetic fields and the coils and whatnot is basically the same. But then once these wires come off here, what we can do is we can construct clever devices that switch which wire these cords are connected to every half turn. And so what that's going to do is it's going to take our old alternating current and it's going to make it look like this. And there you can see you've got a much flatter looking voltage, although it does have these dips here. And the way you can fix that is you can put in extra coils. So you might have back in your generator, you might have another coil that's at right angles. And the currents are going to come out of phase with each other, so they're going to look like this. And if you're really careful, you can organize them to add together such that you get a very smooth current indeed. DC and AC motors are just the exact reverse process. If we look at that coil in the magnetic field, instead of using force to turn the coil to try and make electricity, I'm going to apply electricity to try and cause a force. So I'm going to put a current through it. So the current's going to be coming out of the screen here and into the screen there. It's going to be the same current because it's going around that coil. And we can see that there's going to be a magnetic force on it. So we're going to use the right hand rule to try and figure out the direction of that force. And so we'll do that one first on the left. Okay, so we take the fingers of our right hand and we point them up out of the screen to be the direction of the current, and then we swing them round into the direction of the magnetic field. And then our thumbs are pointing up, and so that's the direction of the force. And on the other one, we're going to have our fingers pointing in, and then we're going to swing them round to the magnetic field, and so our thumb is pointing down, and so that will be the direction of the force. And so if this is two sides of the coil is going to start to rotate. It's going to have a force turning it around. It's going to have a torque trying to make it go around in a circle. And that's just what it will do. When it gets all the way flipped over, the forces are going to be slowing it down again. And so if we're clever and we use alternating current and we swap the sign of the current, then it's going to be still pushing it forward. And then the current will swap sign again and it'll keep pushing it and pushing it and pushing it. And that's how an AC motor works. If it's a DC motor, then the current coming in is constant, but we use a special tool to swap which wire it's connected to each half turn, and then we get the same effect as the alternating current. And that's how a DC motor works.